Hello, in this lecture, we'll define turning angle of a unit speed curve. After that, we'll see that the sine curvature of a unit speed curve is equal to the rate of change of the turning angle. And then we'll define rotation index. Okay, so then let us begin. So let us start with the unit speed curve. So let gamma be a unit speed curve in R2. So the direction of the tangent vector gamma dot s is measured by the angle phi s such that this gamma dot s is equal to cos phi s comma sin phi s. So this phi s, so it will be called as the turning angle. Okay, so before defining this turning angle, so let us see a proposition. So let gamma be a curve defined on the open interval AB into R2, and gamma is a unit speed curve. So let gamma be a unit speed curve in R2. Okay, so let S naught belong to AB and let phi naught be a number such that gamma dot S naught is equal to cos phi naught comma sin phi naught. So this we can write because norm of gamma dot S naught is equal to 1. So it will be equal to cos phi naught comma sin phi naught for some number phi naught. Okay, so then the claim is, so there exists a unique smooth function phi defined on this interval AB to R such that this phi of S naught is equal to phi naught and gamma dot S is equal to cos phi s comma sin phi s. So for all s in the open interval, AB. So this gamma dot S is equal to cos phi S comma sin phi S for all S. So this phi S, so this will be called to be the turning angle. Okay. So now how do you prove this thing? Okay. So we need to find this smooth function phi such that gamma dot S is equal to cos phi S comma sin phi S. Okay. So let us take this gamma dot S to be equal to Fs comma Gs. Okay. All right. So this gamma dot S is equal to Fs comma Gs, and gamma, it is a smooth function. So gamma dot S, it is a smooth function. So F and G, again they will be smooth function, real valued smooth functions. So gamma smooth implies F, G are smooth functions, and norm of gamma dot S is equal to 1 means square of the norm will be again equal to 1. So this will imply that F square plus G square is equal to 1 for all S in the open interval AB. Okay. So now how to find this phi? Okay. So we can do a back calculation. So suppose this Fs is equal to cos phi s. So we need to find this phi s, and Gs is equal to sine phi of s. So f prime s, so this is equal to minus sine phi s times phi prime s, and g prime s, so this is equal to cos phi s times phi prime s. Okay, so now from here, so this phi prime s is equal to, so what we can do here, uh, so this we can, so f prime s we can multiply it by minus sine phi s, yeah, and uh, g prime s you multiply by cos phi s. So this phi prime s, so this will be equal to this identity, and minus sine phi s is nothing but gs times f prime s plus cos phi s fs g prime s. Okay. So therefore, so this phi prime s is equal to this right hand side, which is again a integral function of s. So you can integrate the right hand side. So from here, so you can get phi s, so which is equal to your, yeah, so here this minus it is there, so which is equal to your this integration s naught to s f g prime g f prime at the point s ds plus phi naught. Okay, so uh, so by back calculation, so I'll get this phi. So now what you do, so you just define phi is to be equal to this. So you define phi is to be equal to this. And okay, so we know that f and g are smooth functions. So f, g are smooth functions. So this will imply, so phi is also a smooth function. Okay. Okay. So we have defined now this phi to be equal to this. And now what we have to show that small f is equal to cos phi s and small gs is equal to your sin phi s. So this we have to show. So then what you do, so let us take, so let capital Fs to be equal to, so capital F is this function, Fs times cos phi s plus Gs times sin phi s, and let capital Gs to be equal to this function Fs times sin phi s minus Gs cos phi s. Okay. So now what we'll do, so you take the derivative. So take the derivative of uh, f and g. Okay. So if I take the derivative of f prime f, so what we'll get? So this will be equal to your uh, f prime s cos phi s uh, minus f of s sin phi s times phi prime s plus g prime s sin phi s plus gs cos phi s times phi prime s. Okay, so you'll get this thing. So therefore, this f prime s is equal to uh, f prime s plus gs times phi prime s whole multiplied by cos phi s plus g prime s minus fs phi prime s times sin phi s. Okay, so we got this thing. So now if I take this f prime s plus gs times phi prime s, So note that this phi of s is this integral here. So therefore phi prime s is equal to, so phi prime s is equal to fs times g prime s minus f prime s times gs. So from here, okay, so now if we substitute this phi prime s here, so what we'll get? So f prime s plus gs times this. So we'll get this thing. So now this is equal to f prime s plus fs times gs times g prime s minus f prime s gs square. So we'll get this thing. And so this is again equal to f prime s times 1 minus g square plus fs gs times g prime s. Okay, so now we know that fs square plus g square is equal to 1. So therefore what we have here, so this will be equal to f prime s times fs square. Plus fs gs times g prime s. Okay, so we have this thing here. So this again you can take this fs common. So this will be fs times f prime s plus gs times g prime s. Okay, and this will be equal to 0. Why? Because this term is 0. Why? This term is 0. So again, so we have this fs square plus gs square is equal to 1. And now if I differentiate with respect to s, so what we'll get? So fs times f prime s plus gs times g prime s is equal to 0. So this will be equal to your 0. So similarly, so g prime s minus fs times phi prime s is equal to 0. So this shows that this f prime s is equal to 0. So this implies that this function f is constant. So f is a constant function. And what is the value of f at the point s naught? Yeah, so it will be so f s naught times cos phi s naught g s naught times s phi s naught. and phi of S naught is equal to phi naught, and f of yeah, so f of S naught is also equal to cos phi naught. So this will be equal to cos phi naught square plus sine phi naught square is equal to your 1. Okay. So therefore, because f is a constant function, so fs equal to 1 for all s. So this we have shown. So similarly, uh, so g, you can show that it's a constant function. So g is a constant function. And this function, so it is equal to 0. Okay. So this implies that so because of this, so f is equal to constant function 1 and g is equal to 0. So this will imply that so f is equal to cos phi s and g is equal to sin phi s. So f equal to 1 and g equal to 0 implies that fs is equal to cos phi s and gs is equal to sin phi s. Okay. So now we got this function phi, and now so our next job to show is to show that this function is unique. So we'll get this function phi to be a unique function. So if psi is another smooth function with psi of s naught is equal to your phi naught, and gamma dot s is equal to cos psi s comma sin psi s. So then what? So then so cos psi s comma sin psi s. So this ordered pair is equal to cos phi s comma sin phi s. So this implies that so if I take this difference of psi s and phi s, so this will be integer multiple of 2 pi. So ns times 2 pi, where this ns is an integer. Okay, so now note that this function, so psi minus phi, uh, it is a continuous function defined on this interval 2r is a continuous function. And so from here, so the image of the psi minus phi, it is a discrete set, and because it is a continuous function defined on the open interval AB, so the image will be connected. So uh, so the image of this function, it will be connected, but the image, it is a discrete set. So only possibility is that so psi minus phi is a constant function, and so there exists an integer such that psi minus phi is equal to 2n pi, or psi s minus phi s is equal to 2n pi. So this n will work for every s. So we have this thing, and so also we have that psi of S0 is equal to phi 0, which is again equal to phi of S0. So this will imply that psi minus phi at S0 is equal to 0. So this will imply that, so this n is equal to 0. So therefore, so this implies that this psi is equal to phi. So these two functions are same. Okay, all right. So now definition. The smooth function, the unique smooth function what we obtained for this unit split curve, the smooth function phi is called the turning angle is called the turning angle of gamma, determined by the condition phi of is not equal to phi naught. Okay. So now, what is the relation between this turning angle and the signed curvature? So let gamma be a unit speed curve in R2, and let phi s be the turning angle of gamma at gamma s. Okay. So then the signed curvature Ks is equal to d phi ds. Okay. So thus the signed curvature is the rate at which the tangent vector of the curve, so is the rate of rate at which the tangent vector of the curve rotates. Okay. And so what is the proof of this? So phi, it is the turning angle of this gamma. So therefore gamma dot s, so this will be equal to cos phi s comma sin phi s. And now you take gamma double dot s. So this will be equal to minus sin phi s comma cos phi s times this phi prime s. So this phi prime s, I'll write it here. This is a scalar multiplication. And observe that so suppose this is my curve and this is my unit tangent vector, which is gamma dot s is equal to cos phi s comma sin phi s. So this normal to this gamma dot s ns, let us write it as capital N. So capital NS, which is obtained by rotating, so this tangent vector by 90° along the anti-clockwise direction. So this normal vector, if I rotate by 90 degrees, so this will be equal to minus sin phi s comma cos phi s. Okay. So now from this equation here, so what we'll get? So gamma double dot s is equal to phi prime s times ns. And this gamma double dot s, so this we know, so this is equal to ks times the normal vector and s. So k is the sine curvature, so this implies that this ks is equal to this phi prime s, which is nothing but d phi ds. Okay, so therefore we have shown that this sine curvature is equal to uh, d phi ds. Okay, so as a corollary of this, so what we can get is the following. The total signed curvature of a closed curve in R2 is an integer multiple of 2 pi. Okay, so by a closed curve, I mean, so end point of the curve will be same as the starting point. So this is an example of closed curve. So now, if I take the curvature at each point, so this is my, say, suppose this curve is my gamma, this is my gamma s. So suppose I take the sine curvature ks at the point gamma s, and now if I integrate along this curve, so suppose this is my curve gamma, so if I integrate, so this will be equal to 2 pi n for some integer n. Okay, so this will prove with the next class. Thank you.